Hello, in this video we're going to start looking at how to multiply vectors together. Turns out there's a couple ways to do that depending on if the result needs to be a scalar or a vector. Let's look at the case where we want the result to be a scalar. That's called the scalar product or the dot product because of the symbol we use to represent the multiplication. So a dot b is equal to the magnitude of a times the magnitude of b times the cosine of the angle in between a and b. And so that's a handy thing. So let's put that in a box. There we go. And reminder that the angle here, I'm still in some kind of weird mode. There we go. The angle here is the angle between vectors a and b. So let's think about what that would look like. So we have vector a, we'll have vector b, we've got some angle in between them, phi here, and we have a cosine of that phi. So what that does is it takes the adjacent part of one of those angles. So if we had a 90-degree angle here between, let's say, vector a and vector b here, we've got this projection. Well, this distance is going to be equal to b times the cosine of phi. So what we do here is we take a and we multiply it with the part of b that's in the same direction as a. That's what the cosine phi does, is it projects the one vector onto the other. So it's one vector times the part of the other vector that's in the same direction. And I want to emphasize here that the result is a scalar. So even though you're putting two vectors in, you get a scalar out. Also, it's worth noting that a dot b is equal to b dot a. And you can verify that with your picture here over on the left, that if you instead projected a onto b and then multiplied it by b, you would get the same result. In other words, the scalar product is commutative. Now let's look at what this would do to unit vectors. So since cosine of 0 degrees is a special angle, since that's equal to 1, and since the cosine of 90 degrees is equal to 0, that tells us all we really need to know about the unit vectors. So if I took I hat dotted with I hat, that would be equal to the magnitude of I hat, which is 1, times the magnitude of I hat, which is still 1, times cosine of 0 degrees, 0 because the two vectors are in the same direction, and this is the angle in between the vectors. So that's 1 times 1 times 1 is equal to 1. So a unit vector dotted with itself is equal to 1. That's true for I hat and I hat. It's true for for j hat and j hat, and it's true for k hat and k hat. On the other hand, what if we mix up our unit vectors? What if we do I hat dotted with j hat? Well, that would be equal to 1 times the cosine of 90 degrees, which is equal to 0. And so mixing your unit vectors, I and j, or j and k, or I and k, that's going to give you 0. So we can use that now to write a general rule for our dot products. So if we're going to work in terms of unit vector notation, and using those rules we just figured out, a dotted with b is equal to axi hat plus ayj hat plus azk hat dotted with bxi hat plus byj hat plus bzk hat. And now let's just distribute that multiplication out. It's going to produce a ton of terms. We just need to do this once though, because we want to see how this is actually going to simplify quite a lot. So we'll have axi hat dotted with bxi hat is the first term. So that would be equal to the magnitude of the first ax, the magnitude of the second bx, times whatever we get when we dot I hat with I hat. And what we get actually is 1. And now we'll add that in to the next term. So ax I hat with by j hat. So that's ax times by times I dot j, which is 0. So that term actually canceled out. And in fact, almost all of the terms cancel out. So we'll end up then with the last one here, ax times bz, I hat dotted with k hat is 0. And then we have ay times bx, j hat dot with I hat is 0, plus ay times by, j hat dotted with j hat is 1, plus ay bz, j hat dotted with k hat is 0, and one more row to go. Az dotted with bx, so we got that, or az times bx, and then we have k hat dotted with I hat is 0, plus az times by, k hat dotted with j hat is 0, and then finally az bz, k hat dotted with k hat is 1. Okay, so the only terms that survived were, there was sort of a diagonal line here. And notice the pattern they have. We need to have an I and an I, a J and a J, a K and a K. So what we're left with is the nice little relationship that A dotted with B is equal to AX BX plus AY BY plus AZ BZ. And let's say that's box worthy. Oh, it didn't turn into a box. There we go. Ta-da. Okay. I did some weird stuff with my earlier writing, but oh well. That's PowerPoint for you. And a reminder that that is a scalar. There's no I's or J's or K's left over. We've already dotted them in. And so it's a very common mistake that you might be tempted to write in an I hat, a J hat, a K hat. That's not right. It's just a number. So let's try an example, and we'll get just a number when we do our example. So our example is let's call vector A equal to I hat plus 2j hat minus 3k hat. And for vector B, we'll use 2I hat plus j hat plus k hat. And let's find A dot B. So A dot B is equal to AX BX plus AY BY plus AZ BZ. So that's equal to, the X component is 1 for A and 2 for B. The Y component is 2 for A and 1 for B. And the Z component is -3 for A and 1 for B. So that's equal to 2 plus 2 minus 3 is equal to 4 minus 3 is equal to 1. Okay, so that's the dot product with A and B. It's just 1. No angles here. No vectors, just scalar. Let's look at another case where dot products come in handy. Let's suppose we want to find the angle in between A and B. The same A and B that we had above. You might wonder, how would we do this? I mean, you could do it by drawing A and drawing B and then using perhaps some trigonometry figuring out the angle. That's actually quite a painful thing to do, especially since these are three-dimensional vectors. Well, it turns out there's a nice easy way to do that using the dot product. So Since a dot b is by definition equal to a times b times the cosine of the angle in between them, we have a way to find that angle. So the cosine of that angle is equal to a dot b divided by a times b, where I mean here the magnitude of a and b. And so the angle is equal to the inverse cosine of a dot product between the two vectors divided by the magnitude of the two vectors. So it's kind of a handy little relationship. So we need to know what the magnitude of a and the magnitude of b are to figure out what our calculation is going to give us. So the magnitude of a is equal to the x component of a squared plus the y component of a squared plus the z component of a squared. Okay, and that ends up giving us 3.74. For b, same pattern. Take the x component and square it, plus the y component and square it, plus the z component and square it. That's just the Pythagorean theorem in 3 dimensions. Same pattern as it is in 2 dimensions. And we get 2.45 when we do that. So we can plug that in. We know that a dot b is equal to 1. We just figured that out. And then we divide that by 3.74 and 2.45. And we get phi is equal to the inverse cosine of 1 on those two numbers, 3.74, 2.45, is equal to 83.7 degrees. And so there you have it. That's a way to find the angle in between two vectors. Now in physics, the next place we're going to see scalar products showing up is when we talk about work, where we're going to actually need to use, we're going to need two vectors and the part of one vector that's in the same direction as the other. So that'll be a little while before we see it again, but we will. All right, until next time.